Yeah, I just created the section at the top. Please sign in. Ooh, we've got shamrock emojis now. That's awesome. Feel free to add some topics at the end. I don't really have a plan. I've got a presentation that I'll probably be jumping around randomly between that and a whole bunch of demos of some of the cool stuff we've been up to in the SigStore project. So yeah, feel free to jump in and ask questions at any time once I get going. We've got a bunch of demos I'm going to try to cover in random orders. So we can focus on whatever people want to talk about here. And then I've got the slides we can refer back to as we go, rather than make everyone sit and watch the whole presentation. Let me set up the screen sharing. People can see.
Yep.
All right, get rid of this little hide thing. Terminal is good. See here?
Yeah.
All right, let me just get stuff cleaned up, and then we will start talking about signatures and open source and stuff like that. All right, ready to go, or should I wait another minute?
I mean, I have 5
All right,
after. I think
let's
you can
go.
go ahead.
So today I'm going to be talking about SigStore. SigStore is a new project Luke and I and a bunch of others from this call and from outside of this call have been working on as part of the Linux Foundation. It's a bunch of different things, and I've had a hard time actually explaining all of them all at the same time. So I think it's easier if we explain it in different pieces. Here's the website though, sigstore.dev. Take a look. The code is all at github.com/sigstore. There's three main parts that we're going to be talking about today, showing how all of them fit together and kind of building up piece by piece to also understand how they can be used separately. Cosign is the first one that I'm going to start with. Probably it's a tool to sign container images. And then I'm going to show how that works with a whole bunch of cool technology like transparency logs, like the Recore transparency log, as well as a PKI and rootCA service we're also working on here called FullCO to manage keys and identities and all of that stuff. Sound good? Okay. I'll take silence as a yes. So most of this, I don't want to bore everybody with all of these slides because most of it is stuff that we've covered in this working group before and learned from this working group and was motivated by all the different presentations we've had over the past 6 months or so.
Dan, if I could interrupt, where are the slides so we can stick that into the notes?
Good question. Let me figure out how to share, and I think I have to do this funny dance to share them publicly. So let me switch that up. I think I can do it with the whole group actually now.
Yeah, you can at least make commentators.
Yeah. Share. What do we call this? This one. If I share with here, everybody in this group can see it. So join this group rather than hitting the request button. There we go. So I can't just share it with the internet. Link into chat. Sorry, I should have done this before. And we'll get that added to the minutes too after. All right, so SigStore. The idea is we want to make it easy for people to start signing their code. Why? Code signing is good, but it's hard. We've seen this before in this group with all the different open source projects and language package managers coming and talking about how they support code signing, how they don't support code signing, why they don't, and all of that stuff. This is what it looks like for language package managers. We've had some of these people like the PyPy maintainers come and present. We've had people talk about signing containers specifically too, but this is kind of just a quick survey if you go to all of the package manager websites and see how stuff is signed or not signed. PyPy's got signatures supported, but they're not really documented. You can kind of just upload a PGP text signature next to your artifact and then tell your users what public key to use and where to find that signature, and sometimes it's there. I haven't found many of them. NPM doesn't support signatures today. The whole repository kind of signs things, but it's different from developers signing things themselves. Maven Central requires signatures in a lot of places. I've seen people use PGP and X509, but I don't know exactly how that's enforced or what you do with those keys. I think you can just use self-signed stuff if you want to. Containers, we had a presentation last time about some work going on there. They're not really signed today, is the TLDR. Go doesn't really have a package manager, so it's not really applicable. You can sign commits if you want to, but there's no real plumbing through the Go tooling for that stuff. Ruby supports them. It's actually got a pretty cool system where you can put certs into your packages and then configure routes that are trusted as part of installation. But nobody's really using it, and the only stuff I've seen is self-signed certs, etc. So it's not really there yet in incentive languages. We'll talk about why and some stuff we're going to do to fix that in a bit. Other projects that aren't languages. We've had people from the Linux kernel and Node.js come talk to us. This is how they sign their releases. They've been doing this for a little bit longer than the languages, and the trade-offs are a bit different, and they all have kind of elaborate systems in place that they've developed on their own. Um, the Linux kernel releases are kind of just source releases that are signed usually by Linus or Greg, and you can find the keys in a bunch of different places that Constantine set up and pointed us to in his presentation, but it's mostly trust on first use after you get their keys. Node.js has this really well thought through system that supports their huge list of maintainers, but it's got a couple problems, which I'll show after this. Despite them trying harder than anyone I've ever seen to support PGP signatures in a giant open community project, it causes a bunch of problems. Kubernetes, nothing is signed in that project at all. They want to start signing and can't figure out how, and we're trying to help them. Python, OpenSSL, if you go through all of these projects and read how to verify stuff, it's usually just a couple PGP keys with the public keys either on a site next to the artifacts or somewhere else. And you can find it there and verify releases if you want to. This is what I was talking about before with Node.js. If you go to their README, there's this long section about how to verify releases. And Miles gave us an awesome presentation about how this works internally for them. But basically, there's a giant list of the keys, the primary keys used for everybody that is authorized to do a Node.js release on this page. And then if you scroll down a little further, you see the list of all of the other keys that might have been used to sign other releases. And they have a verify script to help you verify a release. And basically what it does is pull the trust every single one of these keys that might have ever been used to sign a node release into your keyring and verifies the release against any of these. So if any of these get compromised or need to be revoked or anything like that, you're out of luck because you don't know which one is supposed to be used at any given time. So it means that anybody that was ever part of the Node.js trusted releasers is now part of it forever. It's a big burden to place on people. Distros, these are usually in much better shape, the ones I've looked at. Debian has a really cool system we heard about here too on how they manage which keys get signed by their root keys. They have been experimenting with different ways to onboard maintainers, but historically they've required you to meet other maintainers in person and get your key signed by a whole bunch of them. That obviously hasn't worked out throughout the past year with no one meeting anybody in person. So they're working on some different, more distributed ways to do that. Pretty much everybody here again uses PGP, but nobody is really using trust on first use, or nobody is really using web of trust. They're all using some other key distribution mechanism. FreeBSD has a pretty cool system. They're the only one notably not using PGP for signing. They made their own tool called Signify, which is pretty cool, but it's pretty specific to the BSDs. You can use it for other stuff, but it's not that common. They also have this pretty cool system where they generate the set of keys that will be used to sign the next release at the time they cut this release. And then they put the public keys for the next release into the current release and sign that. So they've got this kind of trusted chain of public private keys. So you can go all the way from one BSD release up to the current one. That kind of scares me a little bit for some other reasons. Like if the releases are a year apart, you know, have to create that private key and protect it for an entire year. And if you lose it or something like that, it breaks the chain and you've got to figure out something else.
Quick
Yeah.
interrupt. I heard secondhand that the Debian folks during the pandemic are using various video call, which obviously can be fooled, but the theory is that's at least raises the bar.
Yeah, I'm sure they figured something out. The presentation we had in this group was a while ago, and they were working on different mechanisms to like use keys for a while and have people vouch for each other and a more pseudonym friendly method by building up reputation over a long period of time too. But it's possible that's changed. That was probably 4 or 5 months ago when they presented. Um, so that was also kind of specific to open source, and this is where things get a lot different. And I promise we'll jump into some demos pretty quickly. But the walled gardens, the app stores, the marketplaces, all handle code signing, but they do it completely differently from open source. It doesn't look anything like the open source signing stuff at all. Um, Windows drivers and Authenticode in the Microsoft Store are probably the most widely known example of this, where they use X509 code signing certs, which are a specific type of X509 certificate you can buy. Um, and you can't ship Windows drivers. You can't install a Windows driver unless it's been signed with one of these certs that's trusted by the Windows system. And they even require the enhanced validation certs for a lot of these Windows drivers, which costs a ton of money. There's a whole identity check and stuff like that from the few providers that do offer these certs. App Store kind of runs their own on Apple. Play Store is similar, but it's all these certificate-based signing things instead of PGP or anything else that we're doing open source. So that said, why is signing hard? And then we'll jump into some demos. There's all these different ways to sign things. Abstractly, this is kind of what a signature is, though. Take an artifact, the person's got a private key, you create a signature from those two things, and then you can hand that to your end users. Once they have that artifact, the signature, and the public key, they can verify that it was signed by the person with the private key. We talked all these projects about why they're not signing. A lot of people think it's hard. It turns out signing actually isn't that hard. It's just that the tooling is all pretty bad and archaic and hard to use today. So we started, it's kind of the reverse order of actually how we wrote all these tools, but this is the easiest way to explain how they work together. So we were kind of focused on containers first because I know a lot about containers and I wanted to make a signing tool for containers. So this is a simple, really, really simple signing tool for containers called Cosign. And it's filled up with other trigonometry puns because of the name. The first version of this tool actually took less time to write than it took me to make this little GIF showing how it works. So this stuff is really simple. Signing can be really simple. Um, the tooling is just kind of bad because it's all general purpose and does a bunch of other stuff today. Let's do some actual demos instead of watching this GIF though and show how Cosign can sign containers today.
Dan, quick question: is there any reason it can't be used for just binary blobs in general instead of containers? Granted,
Nope.
solving containers by itself is a great thing, so it's not a problem if it is limited that way. But
Nope, it can sign blobs today too. The challenge is really about what you do with those signatures after and the keys. Containers have a couple challenges to sign them, but they also have some really cool properties that allow us to automatically store the signatures next to the container and find them and retrieve them later. I actually have some really cool demos though after the container basic one showing some stuff you can do by signing blobs with cosign. Um, so I'll
We're,
do the
we're,
container one. Oh, stop. Go ahead.
oh, sorry. Yeah, I was just going to say quickly, we're working on a Ruby Gems implementation of this, and also starting to look at jar sign as well. Sorry, Dan, you go ahead.
Oh, no. So I just cleaned everything up from the last set of demos. So let's start signing containers. This has the experimental mode turned on, so there's some extra output, and I don't want to try to remember what the environment variable is. So there's some extra output we'll ignore for now, but I'll explain later. So this is, let's get rid of the annotation. This is a public container image. You can look it up, dcr.io. This is just the one I use for all testing. But yeah, it's shared publicly. I'm the only one that can push to it, or probably more people can, but anybody can look at it. So I've got the key. Actually, first I'll show the keys. There is a cosine generate key pair command I showed in the GIF. It doesn't take any flags. It's just one type of key we're using elliptic curve keys. So it generates the private and public key and stores them as files. We can see what they look like here. This is the private key. On disk, it's stored encrypted by a passphrase, which you see we need to enter to do the actual signature. It's encrypted, so you can actually just store this right in your repo. You don't have to worry about committing these. And that allows you to do some pretty cool release flows that I'm going to talk over in a minute. The public key is in here too. This is what a public key looks like. And you can do, we added support for KMS systems and stuff too. So if you don't want to store this and do the signatures locally, you can point at like GCP or another cloud provider's KMS and do that stuff. But now let's sign. Talked about that enough already. We'll get rid of the annotation part for now. No flags, just the thing you want to sign and the key. Enter the password. Now we generated a signature with that and uploaded the signature to the container registry right next to the container. So that's the part that we can't really do for blobs, David, that you were just asking about. If it's just a binary blob, we don't really know where to stick that signature. Certain artifact types have, well-known places for that, like jars have a place you can stick a signature inside of them, Ruby gems, something similar. And we do want to support that stuff, but it probably doesn't make sense to all be in the same CLI. And then forget about this transparency log part for now. We'll come back to it. We can look at the signature. If you know anything about containers or care about how things get stored in the registry, this might be interesting. But the way we do this linking of the signature to the container is a little tricky, but it does work. You can't add something to an image without changing the image's digest, which kind of breaks the whole way containers work. So instead, what we do is make up a funny naming convention. So images can be referenced by their digest. So we make a kind of virtual image to hold the signature that is named after the digest of the thing it is referring to right here. So that is the digest of the container we signed. And then we stick a little cosign suffix on there because other people are doing this same thing. So we can take a look at what actually got uploaded here with the crane tool. And a trigonometry pun to calculate that munging. The command is called triangulate. So that'll just print out this image name that I just showed, and we're going to look at the manifest and run that through JQ. So this is the thing we actually uploaded to the registry. It refers back to the image by its name, and then it's got the signature and stored right here in the annotation. You can't sign a container itself. A container is kind of like a virtual concept until it gets represented somehow on disk. So what we sign is actually a little attestation about that container. It's a little JSON wrapper that contains that digest of the container, this thing here, as well as it's got some other fields where you can stick in optional stuff, which was that annotation flag I showed. We can see what one of those looks like when we verify. We'll get rid of the annotation thing again. So this is going to download the signature from this image, not foo demo. It's going to download the signature from that image and do a bunch of checks on it. So this is the actual thing we signed. We generated this JSON payload. This is called Red Hat Simple Signing Format. They've been kind of the only ones, Red Hat, signing containers for a while now. They made up their own protocols to do it because there wasn't really anything else out there. And here's that digest inside of this that I mentioned. If you don't check this digest, there's nothing actually that guarantees this signature was tied back to the image because the naming convention can be faked and isn't really verifiable. So you've got to make sure to check this. That's what this little log statement is. And forget the transparency stuff for now. So that's signing containers. You can do the -a equals bar, and you can tack on some annotations that get stuck in this optional section here if you want to. Then you can verify against those as well. You can sign something multiple times, and we append all of the signatures. So right now it's actually been signed twice, but since I passed the foo equals bar, you only see the one that matches that annotation. Without that, we'll see both. So you can use this to sign containers today. You can do some cool stuff with the optional tags here, like stick in signed timestamps if you want to build up something like the update framework. You can sign Git commits, which is pretty cool for releases. I'll show how that works, and then we can pause for questions because I've said a lot. A little example workflow I put together uses GitHub Actions to build and release a container from GitHub. This one uses the flow where we just check both keys into the repo, and then every time something gets merged to main, we build and sign it with an annotation about the commit that we built at. all inside of GitHub Actions. So what this actually lets you do, which is kind of cool, is from a container image, if you find one on a registry somewhere, you can look up the signatures, see that it was signed at this commit, come back to the GitHub repo at that commit, and the public key is present in this repo. So you can find the right public key to use for each commit in the repo, which is part of the repo itself and the commit. So it's kind of self-verifying in a little cycle there. And then it makes rotation pretty easy, because if you want to rotate and set a new key for the next release, you just update it in Git before you do the next release. And then people can verify each commit as they go along with each build. All right, a lot of stuff about containers. Any questions here?
You say you sign Git commits. Can you demonstrate how that's done?
Yeah, okay, so that's the signed blob stuff. Or sorry, do you mean
Okay.
about this or about some other stuff, like some of the stuff I was tweeting?
No, this I haven't seen. I'm not on Twitter, so I have no idea.
Oh, okay. So we don't sign a Git commit here. What we actually do with this demo is that we stick the Git commit into the using that -a flag.
Okay, gotcha. Right.
So this flow just uses the annotation flag as like a little primitive that you can stick anything into. So if you find that signature, like if I wanted to do that here, instead of -a foo equals bar, we would do something like git shot equals.
Okay, so
What git shot
it was just collision
so,
of
oops,
what
that's verified.
signing a Git commit means in my head. It's not
Um,
actually signing a Git commit, it's signing information about a Git commit.
We'll come back to that in a second. What
Okay,
did I do
all right.
wrong here?
Okay.
Oh, maybe there's a new line in there or something. But anyway, yeah, you should be able to stick that commit in here as an annotation and sign it. Wait, no, it did work. I just don't want to type that to JQ. So the, what we're signing here is a JSON wrapper that includes the Git commit. So the Git commit itself is kind of signed. It's just stored with the container. Now, if we do a verify, see that come out. So what that claim kind of says is that I claimed that I built this container with that Git commit. Does that make sense? This is actually part of the thing that is signed with the key. So we're signing not the Git, we are kind of signing the Git commit itself, but we're signing the relationship between the Git commit and the container image.
Okay.
Does that kind of make sense, Constantine?
Yeah, I just thought you actually inserted into the Git repository, which is why
Okay.
I was confused.
Okay, we can do that one next.
Okay.
Yeah, there's a question in the chat. Let me read it
Sure,
for
I
you.
can't see it.
Yep. Possibly a bad question. What is an example of optional stuff to add?
Yeah, so the field is called optional. I didn't name it that, but yeah, that is kind of what I was showing here with the Git commit. That's one example. With this flow, I have another one here that does a release build where we stick in the Git commit to get signed, as well as the Git tag that the release happens at. So when you create a release in GitHub Actions, this will automatically do all of that stuff. The private key is in the repo, so I forgot to mention this. The only thing that we do is we stick the password into a GitHub secret. So this flow is really designed for, the claim is kind of coming from GitHub's builder. This is coming from GitHub's build system, saying that we executed this with this password, and this is what came out at the end.
And then the second part, I think you well, maybe I know the answer. If company A signs a container and then company B wants to add an optional thing and then sign the container, is this possible? And will company's A's signature be preserved?
Yes, and so that's, yeah, so good question. Yes, and so that's one of the challenges with cosign. You can sign things multiple times, and let me find the section that explains the challenges. You can sign something multiple times, so as long as both companies have access to push these signatures, which probably isn't true, but if you copy the container, normally the way this works is the company publishes the image and then somebody copies it to their own repository where they do have access. They would copy the original signature and then they can append their own onto it in their own repository. It's a little bit racy. That's kind of the challenge with the way the registry works today, is you have to download the thing, append your signature into the list, and then you push it back up. So if two people do that at the same time, it's last one wins. There's some ongoing proposals to add like HTTP tag semantics to the registry API, so you could do optimistic concurrency and detect and prevent that. But yeah, multiple companies can sign things and verify them all later. All right, so now we'll do the transparency log stuff here quickly, and then we'll go to the signing git commits that Konstantin wants, because that's pretty cool. All right, so the transparency log piece. We saw some of that output here. I mentioned when we do a sign, when we do this sign, we are going to see a little output saying that we also uploaded the signature to a transparency log and got an index. So this transparency log I'm referring to is called Recore. I'll jump over here and then show, hopefully the demo works. Yeah, just did, awesome. So transparency logs are a pretty cool concept. You can think of them as a public append-only log. So we were operating one of these as part of this project called Recore, and it stores signatures. These are used across all of the web today for certificate transparency. They're how browsers can prove that certificate authorities are behaving correctly. Recore lets you store signatures in here. And so anybody can look through this log to find all signatures that have been created. What we actually store is kind of a triplet of the signature bytes, the public key that was used, and then the hash of the thing that got signed. It's kind of all the elements we need to verify that it's a valid signature. So one of the cool use cases here is that you can detect, you can use this to help detect key compromise. And so what I mean by that is if you have a private key somewhere that you're using to sign releases, you have to protect that private key. If you lose it, somebody might use it to sign stuff on your behalf and trick your users into thinking it came from you. Today, you really have no way to detect that or mitigate against that happening outside of just protecting your key as closely as you can. What this transparency log lets you do is actually pretty cool, and it lets you monitor the log for your for signatures that came from your private key. And we have a little demo here that shows how that works. I have something running on my own little cluster. There's an example checked in. I'll show you where the code is. It's still in a pull request. Did this a couple days ago. So this is a log anybody can run themselves, or a little service anyone can run themselves that tells the log. It's just 100 lines of Go or so, a couple hundred lines of Go to watch the log, verify the log, and then uses SendGrid to send myself an email anytime my key got used. And then I can make sure that it was something that I actually intentionally signed. So I've got this running right now, and these are all the emails I got during the demo every time I use those keys. So you can see here, it looks safe. This is the entry in the log. I got a little email, and this shows you the command to check it out and see what got signed and what that is. So if we run this, we'll see the entry stored here, or JQ. This is the hash of the thing we signed. We don't store all of it in transparency log because that's kind of scary. We can never delete stuff. The signature itself, this is just base 64 encoded bytes. This is the key type. We also support PGP, all the different ways of signing things. We just have to know how to verify the signature is a real signature. And then the content of the public key for later. So this is how we can make sure and detect our public key being used. This is kind of complicated, and there's a lot of subtleties with transparency logs. Any questions on this one before I go a little further and get to Konstantin's cool Git signing question? Luke, did I miss anything on Recore?
No, it's all good, Dad.
Okay.
Yep.
All right, so now signing blobs, David's original question, and signing Git commits. Actually, let me do one more demo here first, and then we'll get to that. So with all of this so far, you still have the question of getting and managing keys, communicating those keys to your users, not losing the private key, even if you leak it. If you leak it, we can help you detect that. But if you lose it and no longer have access to it, then you've still got to come up with a new one, figure out some way to securely communicate that new one to your users. And for users, they need a way to find out which keys should be used for a given person. And so we thought for a while about how to help solve this problem. and came up with a pretty cool flow I'm going to show here next. If you've got the experimental mode turned on in Cosign, you can try this today, but we can do a signature here of that same image. Delete and clean up quick first. We call this keyless signatures. So we're actually going to sign this image with no keys. Verify it with no keys. See no keys in the command line. We're going to sign this image. All right, so if you've got the experimental mode turned on, this pops up. And let me fix my browser windows. I'll re-open over here. All right, so this is a little off flow. We'll go back to the terminal though. This got popped open when I ran this command. So this is keyless signatures. What we actually do here, if you don't pass a key, is that we generate an ephemeral key pair. So this happens right in memory. It's sitting there in memory right now. They never touch disk. We generate a private key and a public key. And then we get a certificate for that. We talked about how web certificates and transparency logs help with that a little bit earlier. What we need is a certificate that is issued to us as a person. And so we built a little certificate authority that's running and can issue code signing certificates to individual people. If you've ever used Let's Encrypt, they do this challenge to prove that you control a domain or a web address by giving you some kind of random token, and you have to display that in your website somehow. There's a bunch of different ways to do it, as like an HTTP header or a DNS record. But that's how Let's Encrypt can verify the person who wants a certificate for a domain actually owns that domain. We're essentially doing the same thing except for a person. And to do that for a person, we're using email addresses, and there's already a challenge protocol that exists for that called OpenID Connect. So the browser pops open to the OpenID Connect provider. In this case, it's Google. I verify, I click this button to give it access and prove to the CA that I do own this email address at this time. The auth happens. We come back here. And now we sign with that private key, throw it all away so it never touches disk, and enter all of that into the transparency log. So the certificate authority also issued that public certificate and stuck that on a transparency log too. So if we want, we can monitor that one for all certificates that are issued on our email address. In case we ever lose our password and our two-factor auth token and somebody can steal our email address, that's all on a public record too, and we can identify if that happens and find all the things that were signed. So now we can do a verify on that. We're just not going to pass a key anymore. On the image, in this case, we actually store the certificate chain that can be used to look this back up later against the root certificate that we've got. So that's how this is going to work. We're going to verify. Oh no, what happened? No certificate found on signature. I broke something. Oh no. See what's in here. See a certificate. We'll pretend that worked. The demo didn't quite work. Yeah, so we store the full certificate here, which you can download, look up, and verify, and the signature itself to figure out what happened after. And so in this flow, what we do is we download this. What should have happened is that we should have downloaded the certificate, verified that it signed the artifact, the public key in here, and then pulled out the email address and printed out my email address and say I signed it. Does that kind of make sense? Everybody can pretend that the demo worked for me. I do have some GIFs around of it working. That part sort of makes sense so far. I did this demo like 5 times this morning and yesterday, and it worked every time. All right, so now we'll get on to the blobs real quick and how we can do some other cool stuff here. We have a sign blob command here in Cosign. Sign any random thing. You can do it with a key, or you can leave the key off and do the cool transparency log stuff and certificate authority stuff. What we realize here is that we can actually sign anything with this. We just don't have a way to store the signatures places. In some cases, the transparency log might be enough, and that's where I'm going to show the git signing stuff. Let's go back to Cosign. I called this fun.md and just wrote in some Git signing stuff here. There's one more that's sitting in a pull request I'll jump to at the very bottom that shows all of this together. But this shows a couple different ways to sign Git commits. Right? We've seen a bunch of different proposals in this group about ways to improve the way Git handles signatures. I'm going to see how much we could do without having to change Git. If you thought, Git is kind of hard coded today to use PGP, GPG throughout all of the signing and verifying commands, this shows that it might not need to be. So this first one here is cosign to sign a blob, except instead of a blob, we're just going to sign the text of the Git commit itself, that hash with a key. Shows what that looks like, and we spit out this signature at the end. So if you want to, you can send the signature to someone and they can verify that you signed the hash of the Git commit SHA. You can check it here like this, and it verifies, okay. This still leaves you on your own for communicating the public key and signature to people because we're not storing it in the Git repo. Now, this might be what you were asking about, Constantine. Git has this way to attach notes. A lot of people don't know about this command. The Git notes command lets you attach messages or files or objects or anything to another commit in Git. So we can actually just stick this right in the Git repo instead of having to use another storage mechanism. This shows that same thing. It's a mold commit of using Git notes to stick the signature in that we've generated with the KMS or any other system we want to. Just attach it to the head commit. And then you can verify it and look it up later with Git notes show and the commit. This will give you a list of all of the things that have been attached to that commit, and you can do some kind of verification that way if you know the right public key. If you want to make the repo kind of meta and self-verifying, you can again check the public keys into the repo at each commit and ensure that you used the right key to sign each one at the right time, and you can do revocation and rotation that way. Does that sort of make sense, Constantine?
Yeah, it does. There's two comments. One, do not use the default ref for those notes. You can actually create your own ref. So the ref's notes something specific to you. Otherwise, you're very likely to just clash with somebody else's notes, right? And two is generally developers don't really like Git notes because they are a weirdish database that lives in its own ref and doesn't get, unless you're cloning with mirror, nobody actually going to get them.
Yeah, exactly. You have to remember to push them. You have to remember to pull them, so nobody actually has them. There's one cool use case I've seen of this, which is like the Git Appraise project. I don't know if anyone's seen that, where they built this whole code review system on top of Git notes, so you can store all the code review and commenting and issue tracking and that kind of metadata in the repo too, which is kind of cool if you want to move between Git providers, but that has a bunch of problems with the Git model.
Well, this is where we store the tarball signatures for kernel releases too, in Git nodes.
Cool. So some people are using it for this. That's cool.
Yeah. So basically following in our footsteps.
Sort of, yeah. But Constantine said don't store things in Git, so we don't actually need to. Let's show hard mode here. If you turn on our transparency log stuff, what you can actually do is just upload that signature to our transparency log. You upload the public key bytes, the signature itself, and then the thing you signed. So in this case, the only thing you're really uploading is the Git commit itself, because that's the thing we're signing. You don't need to store it in Git if you don't mind sending us the commit hash to the transparency log. You can actually go backwards and look stuff up in the transparency log later. So if you don't want to store it in Git notes or somebody forgot to pull it from a mirror or something like that, you can look it up. So this shows how to use the record command to look up using the search thing. Instead of an artifact, we didn't sign a tarball. All we signed was the Git commit itself. We can get all the signatures that are in our transparency log attached to that artifact. So instead of Git notes show, we're using the transparency log search to do the same thing. And from that, you can pull out the signature and use the public key that you got over email or was in the repo at that right time. And so you can verify all this stuff without having to store anything in the Git repo too. You're uploading the SHA and you've got to access the log in order to do this. But this is a little bit more magical since we're not relying on Git notes. Does this part kind of make sense? And then I'll jump to level 11. No questions? All right. So level 11, I need to merge the last pull request, but I've got a self-verifying keyless assign git commit here. So what I actually did here is used the keyless mode to sign these two commits. The first one had a test failure or a lint error I had to fix. So I had to sign both of these, but I put it here in the pull request message. So this commit was signed with the whole keyless root CA. The signature is stored in the transparency log. So anybody can look this up later and check it against my email address that I went through the two-factor auth flow for and stored in the other transparency log. So you can run this to search for the commit. There were two. This is the first one. Find that entry, and you can download that entry, and you see the certificate that was generated at that time. I think Santiago fixed this up a bit. I don't know enough OpenSSL to do this on the command line, but it's pretty simple to do in Go to actually do all of the verification pieces here. So you can run this through OpenSSL. That's all I showed. And you can see that the email address is in that pull request, and all of that metadata is signed with the public key in the certificate. And then, so you can actually verify that this email address did sign the commit, which also contains an email address right here, but anybody can type anything they want in these email address fields. We've seen a bunch of examples of people doing stuff like sticking Nat Friedman, the GitHub CEO's name, in their commit messages and having it show up on GitHub attached to his profile. So anyone can stick anything they want in these fields. So with this, we actually get some proof that the person had access to the email address at the right time that they signed to this commit. So you can imagine a little GitHub pre-submit bot that checks for signatures like this and prints out a big green extra verified sign. So I think that one's pretty cool. There's some subtlety to the way this works that I kind of glossed over around the short-lived certificates and timestamps. And if the demo had worked, we would have seen some of that output that I could have talked about. But the whole way that we issue these certificates is that we expect them to be very, very short-lived and the private keys to never touch disk. Let me find, maybe there's an example here of outputs. So this is what it should have looked like if the demo worked. We would have seen this. So we check the claims on the signature, we check that they were in the transparency log, and then there's this subtle piece that I glossed over, but it's kind of what ties it all together. And then we see the email address should have been spit out if the demo had all worked. But the timestamping piece is actually pretty critical to making sure all this works. If you generate these keys and throw them away, you want to make sure they're really thrown away and can't be used later. Let's Encrypt does the same kind of thing. They issue certs for, I think it's like 2 months, and then you have to have a system that keeps getting you new ones and refreshing them. That works with browsers because their certificate is expected to be valid when you're accessing the web page. That stops working a little bit for code signing, and that causes a ton of trouble because you sign the code and then it's got to keep running for years. If the certificate expires, then the code would stop verifying, which is kind of problematic. SolarWinds is a good example of this. Not to pick on them, it's more a problem with the current Authentic Code stuff. But their keys were compromised back in December, and they've been unable to revoke them and switch to new keys still, because if they did that, all of the non-compromised builds would stop working. So they need to first track down all of the builds of SolarWinds that they don't want to break and re-sign those with the new keys before they can revoke the old ones. So we're coming up on 4 months since the compromise, and they've still been unable to revoke. So what we do is short-lived certificates. They're only, instead of being valid for years and making sure that they're always valid when you want to use the code, we took a pretty different and somewhat new approach for code signing, where this we required that the signature was created when the certificate was valid, not that the certificate is still valid. There is some prior art for this in code signing today. Authentic Code supports trusted timestamps, and so does JarSign. They're the only tools I've seen that support this. There's a whole RFC protocol for getting trusted timestamps. It's RFC 3161. You can do it with OpenSSL. There's like an OpenSSL TS command where you can generate a timestamp request, just like a certificate request, send it to one of these authorities. And then they hand some payload back to you, which is where it's signed with their public key or signed with their private key, the timestamp itself. So, and the hash of the thing you sent them. So that can kind of serve as evidence that you generated the signature at least before a certain time, which is all we're really doing here. So you can do that if you want to. You can get these little signatures signed by a third-party timestamp authority, but there aren't very many of them. There's only one that I could find that was free. What we realized, though, is that the transparency log also serves as a trusted timestamp source. We have a timestamp at which the signature entry was integrated into the log. So if we can show that the signatures were entered into the log while the certificate was valid, that's good enough. And so we can ensure that the certificates don't get reused later, that all this happened while the certificate was valid. Any questions about that piece?
There's a couple questions in the chat. I think maybe I missed one. I'm not sure if you already answered these. Are multiple container image manifest formats supported for the input to the container signing process? I think you gotta.
Going back.
Or answer these later if you want to keep going.
No, I think there's not too much left. So I'll stop sharing. Where's that one? Or multiple. Okay. I don't know. If you're still on the call, do you have an example of other types of container image manifest formats? I think we only
Sure.
released. Oh, yeah, go ahead.
Yeah, I saw I think in the example you showed in the attestation, it said Docker manifest
I see.
versus like OCI. I was just curious.
Yeah, so that's something we have to change in the payload format itself, get rid of the Docker format. That came from the original Red Hat simple signing spec that they started years ago when Docker was kind of the only one. There's nothing Docker specific actually in there. That's just the name of the key that they expect the signature to be located at. So we're hoping to get that some new format to stick this stuff in that's not quite as custom JSON with names like that in there. So what we're actually signing is the OCI manifest. Well, the digest of the OCI manifest. We then just stick it in another JSON thing that says Docker in the name.
Okay, sweet. So as long as the verifier has access to the OCI manifest, they can do the verification.
Yeah, exactly.
Okay, sweet.
Going down more. Yeah, there's also git-s, which provides more than just the email. Yeah, so that mode of signing uses a GPG key. It's a little weak with GitHub. I don't really like it. It doesn't do a ton because what GitHub does is they show a badge that something was signed, as long as it was signed with a key that is uploaded on the user account profile. The user account profile is protected by a normal password, so anybody with the password can just change the keys that are stored in GitHub to match whatever they have. So unless you're using something like Web of Trust or some other PKI on top of git-s, I don't love it, and it's kind of like this whole self-sign thing where they give you a green badge that might not actually make sense. Yeah, that's what you said in the second half there. Dumb question, lack of familiarity with OpenID Connect. How is it exactly that verifiers are able to trust the signature in the key of the signing process? The email address is legitimately associated with the signature. Yeah, so that's where the transparency logs come in. Our service, and Mike can probably explain this better than I can because I don't really understand OpenID Connect a ton. Yeah, so our service basically verifies that Google or whoever the identity provider in this case says that this key is actually associated with this email address. There's this whole identity token system, and then what we do is we stick that on a log, a transparency log, so anybody can look that up and see all of the certificates we've granted. So if we granted one inappropriately, it's on the public record and somebody can detect it. Just like I showed with the email system for public keys, you could imagine an email system for email addresses where every time we issue something for an email, we send them an email warning them about it. If Google or the identity provider were to screw up, that would still show up through here because the certificate would be issued and be on the log, and we could detect it later. We can't really prevent it. We're putting a whole bunch of trust into your password on your email address and your two-factor auth and anything else you're using to protect that account. But we can provide transparency on all of this so that if anybody does screw up in that process, it's on the record. And then you can tie that certificate all the way through the record log to everything that was signed with it. So you don't have to go through this huge emergency, re-sign everything you might have ever built. You can track down the exact malicious artifacts and figure out what to do with those.
Okay, thanks. That's really cool. So like a company has like an SSO process, they can rely on that and move forward. That's cool.
Yeah, that is one of the big pieces of this trust model. We assume you can't keep private keys private, and we assume you can't keep private keys without losing them long term, but you can probably keep access to your email address most of the time, and there's existing mechanisms to get that back. And if you do lose it, we can recover from it and detect all the bad stuff that happened when somebody did have your password. Did I screw that up, Mike? Did I butcher OpenID Connect?
No, I think you pretty much nailed it. Single sign-on for code signing.
Yeah, that's great. It's kind of like Keybase, vaguely.
It was a lot. I'm still sad the one demo failed.
I have sort of a broad question. You sort of showed a few different ways of storing the signatures, and then you mentioned in passing that for most cases, the transparency log is enough for sort of storing the signature for an artifact. In what cases is it not enough? Couldn't, for basically any artifact, I just take a SHA, look it up in the transparency list and get all the signatures? Why would I ever need to store it elsewhere?
Yeah, so there's a couple questions, or a couple things there, and I think you probably know the answers and you just want me to talk about it, but I'll do it anyway. Yeah, if you, some reasons it might not be enough, if you don't want to store and upload your stuff to our transparency log because you're signing in a private environment that doesn't have network access or something like that, you've got to come up with your own way. It's kind of meta though. If you don't want to put it there, then it's not, you can't rely on putting it there. Searching logs is also not the fastest. You have to tell the log and go through each index if you want to do that search command. We're running an index to make that quicker ourselves. So we're indexing those 3 keys. That index itself is not verifiable. So when you run that search command, it's pretty subtle, the problem there. When you run that search command, if we give you a result, you know that result is correct and it's in the log. But there could be something wrong in that index where we don't give you all the results or we don't give you any results. But if you do get a result, you know that that's on the record. You can't rely on that set being the list of all results though, which does have some implications. You could run your own index though, and we've got some examples showing how to do that if you want. And there are ways to make indexes like this verifiable. We just haven't done it yet. This is all based on the Trillion open source transparency log project. And we're using transparent logs. They also have things like transparent maps where you can make those guarantees quickly, but they have some other trade-offs we have to work through. There's one more though, which is, like you said, if you have an artifact, you can find all signatures associated with that hash. That's correct. What we want to do though is be able to provide a list of all attestations made about an artifact, and we can't do that today, and that's a little subtle. Attestation is kind of a weird word. What I think of it as is a signature with about an artifact with a bunch of other metadata. The payload that we actually sign and cosign for a container image is an attestation. We're not signing the container image itself, we're signing a little JSON wrapper with a reference back to that container image and then some random claims that you can type in. So the hash in the log is not actually the container anymore, it's the hash of that JSON. So if you have a container and didn't have that funny little naming scheme to find those, then you wouldn't be able to look up all signatures for that container. Because we don't store the whole JSON, we only store the hash of the JSON, and you can't reverse the hash function. So we have some other cool ideas too on how to start storing the attestations completely in a way that we can index and do all sorts of cool linking throughout the log. But that's scary because we don't want to allow people to put anything they want in the log, because then they can put bad things in the log and we can't delete it. So there's some ideas on storing those in a separate content addressable store referenced by their index so we can blow stuff away if we ever have to. Lots of stuff. It's been fun.
That's a good answer. I'm satisfied.
So there are restrictions on what you can put in the log, right? So you can't just easily poison it by putting illegal content in there, right? What provisions are there to prevent this?
Yeah, I'm sure we're not perfect. The only things we store in the log right now are signatures, public keys, and hashes. We store a whole bunch of different types of public keys. If it's just like an ED25509 public key, it's pretty short and just bytes. And we do verify that the stuff actually signs with it. So you can come up with some way to encode bad stuff in the number of bytes that we allow. Then yeah, that's bad. I think we do support other stuff like PGP signatures, which are always store the PGP public key. Santiago has told me some horror stories about different ways you can hack PGP to stick bad content inside of different fields in a PGP message that he's done some fun experiments with. So I'm sure we've got to do some more work there to make sure we're stripping stuff out of the keys themselves. But outside of the hash and the signature, that's really the only way you can get stuff in.
You can attach a JPEG image to a public key, right? It's supposed to be your face, but it could be anything, right?
Yeah, in PGP, you can do some crazy stuff. We do try to canonicalize and strip stuff out. So we're just looking at the bytes themselves, but I don't know the PGP protocol that well, and I'm sure we're making some mistakes. Luke dropped in some of the other types we support too.
So of course, then the question is, if we do miss something and somebody does poison the blockchain, what do we do?
Yeah, I don't think anybody really knows the answer there. You could do the same thing with certificate transparency today too, because they store entire certificates. And if you can get a certificate signed, you can get a lot of stuff in an X509 thing. I don't know how they handle it. I think kind of what they would do is stop it as soon as cut off the log at that point and start a new log from there without the thing if they really had to. But yeah, for now, we're not making any promises about keeping this log around forever. It's just a sandbox playground. And we do want to get a little stricter there. If you can think of ideas on how to stick stuff in the log, please try and tell us, and we'll try to fix it.
How would it scale to somebody doing it, for example, 1,000 signatures a minute, whatever? How fast, how large is it going to get, and how easy is it going to be to search it? Is it going to be progressively slower and slower?
Great question. Basically, we're not inventing anything here. We're kind of just copying WebPKI, which scales pretty well. I've looked at a bunch of the numbers. I haven't done any load tests myself, but Let's Encrypt shared, the cost and operation of their transparency log for certificates, and it all seems pretty reasonable. They cut off once a year and start again with a log of 0, so you know which one to look in if you know what year the thing happened in. But their bill was incredibly reasonable for all the certificates they've issued on an annual basis. And they just did something like 200 million in a day a couple of weeks ago and wrote a whole blog post about it because they had to re-sign things a bunch of different ways to make them keep working with old versions of Android or something like that. So 200 million a day, I don't know what that comes out to per second, but that stuff all works fine without any concerns.
I know, I approve their bills, and I'm not sure those are reasonable, but I guess Google has different ideas of what is reasonable and what isn't.
There is so certificate transparency sits on top of Trillium. So CT is called a personality and recalls a personality. So it's a sort of front-end interpretation of Trillium. And they got a project called, or some code rather, in Trillium called CT Hammer, which they use for load testing. And that's hit thousands of seconds. But that's dealing with certificates. But it's not too different what we do. I mean, we're doing the same sort of thing. We're validating the sign-in and then queuing the leaf for entry and then ensuring that it's actually entered into the log. So it's pretty performant. They got one running at Let's Encrypt run a CT log, Cloudflare, Google, Facebook. There's a few of them.
Yeah, I put that in the category of problems I would love for us to have if thousands of developers start signing things at the same time. That'll be awesome.
Sure.
Is that a challenge?
Please. We can always throw some quotas on your public key, Konstantin.
Okay.
I have another question if there's time.
Yeah, one more and then I have to run.
Sure, and you may have covered this already. I'm kind of just diving in here, but you showed a good example of how you would take a container image and do the whole signing and verification process. How does this end up getting applied to other deliverable formats, like different language ecosystems and that sort of thing?
Yeah, we've just started looking into this. Ruby, I think, is actually just going to be plug and play almost because they have this cool way to stick certificates and signatures into a gem and then configure all of their tooling to look at different routes and do verifications against that. So we have to try it, but they already have this in place. Java does as well. If people don't have it in place, then they can rely on the transparency log for now. But we do kind of want to work with different ecosystems to figure out ways to include this right in the image to avoid having to query our log constantly. So,
okay, cool.
Yeah.
Thank you.
All right. Thanks, everybody.
I just shamelessly plugged Dan's blog post from last night that talks about a few different ways how you can see this being used in practice. I'll put it in the notes too.
Thanks.
Bye all. Take care.
Thank you. Bye.